Balancing, wanted to do a balancing one really badly. There are some hard ones in the reader. Was there a really fun one you found? If not, I might be able to find one. Way back there.
Number 18 on page 47.
Tell me the page.
47.
47. Let's see if that one was fun. You looking at this one?
Yes.
This one we did in class, so I won't do that one. Take a look in your notes. We did, yeah. 21. 20. Okay, let's see if that one was fun. This one's decent. That one, the uranium one?
Yeah.
Okay. You can ask me more later if you want, but let's try the uranium one right now. Okay, first of all, I see one of these. It doesn't look totally straightforward, and it's a 4 or 5 point problem all by itself. This is one I'm going to do last on the exam. I know I'm giving you a tough one, okay? Second, because I don't know the level of toughness, let me write this out. HNO3 goes to UO2 NO3 2 plus NO2 plus H2O. All right. Because I don't know the level of toughness, I'm going to get another color out for scratch. I'm just going to put variables here. A, B, C, D, E. When I'm approaching a tougher problem, it's just easier to put variables there. And you'll see why. Okay, now I'm just going to go through the different atoms that I see. There are elements. So for example, uranium on the left-hand side is 3A. You see that? 3 times A. On the right-hand side is just C of them. Okay? Now let's pick another element. Let's say like nitrogen. On the left-hand side, how many are there? Just B. On the right-hand side, there are D plus, 2C. 2C. Okay, now you go to the next element. Let's try hydrogen. Okay, hydrogen on the left is B. On the right, we're doing hydrogen, right? Yeah, 2E. Is that okay? All right, did I leave any? Oh, I didn't do the hard one. Oxygen. Okay. On the left, there's 8A plus 3B. Okay, now the other side. There's E. I'll work my way backwards. There's 2D, and there's what? How many C's? 8. Yeah. 2 here and 6 here. So that's a total of 8. Perfect. I have, and did I miss any of the elements? No? I got all the elements? All right, well these two are equal to each other. These two are equal to each other. I basically have 3-ish, 4-ish equations and 5 unknowns to solve. Okay, sweet. So what I usually do, now you could have done it by inspection for sure. I think when I first did this, I did it by inspection. I later realized I got a little lucky when I was solving it. This problem was a little harder than I realized. Things like that happen. But usually now, these days, I solve it like this. It's just a sure way to get to the answer. Okay, then I look through each of these and see what variable is kind of the most present variable. What do you think? Which variable? A, B, C, D, or E? C is present only here and here. Oh, and here. Yeah, it's present 3 times. That one's pretty good. Or B is pretty present. Which one's your favorite?
B.
Okay, it doesn't matter, but. Okay, so I'm going to go through now and rewrite these all in terms of B. So that one's in terms of B. That's in terms of B. Let's write this one in terms of B. Okay. 3B equals 8C plus 2D plus E minus 8A. Okay, now I know a lot of these are equal. So for example, 3, I know that B equals 2E. I can plug that in here. B equals 2E or 2 equals B. So I could say something like, this is, if I put E in here, what would it be? Yeah, 6E equals 8C plus 2D plus E minus 8A. So I can move the E over, 5E equals 8C. Huh? Oh, yeah, can't see it. 2D minus 8A. Okay, so that's one thing I can do to kind of solve this a little bit. So I have this in terms of E. I can also toss this equation in here. So how many A's would I have if I toss this equation in here? 24A plus 2D minus 8A. So this is going to be 16A plus 2D. Now we're kind of getting somewhere that's a little more useful. And let's see, is there anything else that'd be helpful to toss in here? That's probably okay for now. Okay, so now I have a couple equations that are set equal to B pretty reasonably. Now I'm going to go back to my reaction. Okay, and let's use brown. Okay, let's pick an element that appears only twice. So probably uranium is a good one. If A is 1, and so C must be what? 3, right? Is that cool?
Yeah.
Okay, there's 3 on each side. Okay, so that means A is 1, C. So what is E? If B, oh, yeah, we don't know B yet. I'm going a little crazy here. Okay, but if A is 1, then, and I know C, oh yeah, C is BA, okay. So this one I could say B equals 2C, 2 times 3 plus D, or it's 6 plus D. What else do I know? And then over here, what else can I say? 16A, if A is 1, that's 16 plus 2E is 5E. Right, if A is 1. Okay. Okay. Yes. I picked it. How did I know A was 1 was the question? Yeah, I just picked a variable to start with, where it only appears twice on each side. Yeah, so it kind of starts to knock out some of the variables. I could have also started with B or E, since H shows on one side each. Yeah. I'm just kind of looking for a whole number that I can put on both sides. Okay? Okay. All right, so let's see what I'm left with. I've got an equation. I got this equation, and this equation. It looks like I'm getting pretty close. This has a D and a B in it. Okay, so let's rewrite the equations I have. I've got B equals 6 plus D. I've got 5E equals 16 plus 2D. And I've got B equals 2E. Okay, I've got A equals 1 and C equals 3. Okay, so right now I have 3 equations left and 3 unknowns that I need to solve for. All right, let's start working on that. So if I can plug in here 5E, B over 2, equals 16 plus 2D. And then so 5 halves B equals 16 plus 2D. And that's from this equation and this equation. Now I have 2 equations with a B and a D in it. So I'm going to put 16 plus 2D. D is B minus 6. Or 16 plus 2B minus 12 equals 5 halves B. B over 2 equals 4, or B equals 8. There we go. Now we have B. So I'll go back. B is 8. No? Okay, you're thinking. B equals 8. E would have to be 4. I think I pretty much got them all now. And D would have to be 6 less 2. Yeah. We got all of them? Yeah, there we go. 1, 8, 3, 2, 4. So just kind of messing around with algebra. This wouldn't be the only way to solve it, but it's kind of the way. This was a pretty tough one. I would agree. It looks like a short equation. Some of the longer reactions are actually easier sometimes, but this was a pretty tough one. So I just did a bunch of substitutions so I could get it. Okay. What about redox? Can you use the redox method to solve it? You can try and show me afterwards and see if it worked. I'm not sure how you would do it at this moment. Okay? You do read that and work on your 7th grade algebra. I understand. Okay, I'm gonna move on. Okay. Yeah. What's up? Does it always turn out that this is 1? I look for usually the most unusual element, and that's the one I like to start with as opposed to say the H. It's not always true that this will be true, but you know it's in a 1-to-3 ratio. So for example, if I got like 8/3 here, I would just multiply it through by 3 at the very end, and it wouldn't be a big deal. So it's fine to totally start off guessing something. Yeah. Okay, let's see what else we're going to work on. Limiting reactants. I think I had a problem set. I forgot where it went though. Let's see. Problem was going to be limiting reactants. On page 44. Is that where that was? I lost it. I had one. I don't know where it disappeared to. It was on the same page as the Dianable. 20. Yes, ish. That's a great one. This is page 26 of the reader. Number 21, page 26. Okay. All right, I know this is a limiting reactant problem because I have information connected to moles that can get me to the answer. So this question is over-specified. I have too much information. So I know it's a limiting reactant problem. The first question is what mass is produced. It's going to be whichever one is the smaller answer. So I'll need to go 0. If I start with iron first, 0.150 moles. I know there's 2 moles of the Fe2O3 or the iron 3 oxide for every 4 moles of the iron. And the last step would be the molar mass of this. Let's see if I have that written down anywhere. It is 159.69 grams per mole. Okay, that's with the iron. I'd also have to do the same with the O2. With the O2, I'm starting off with mass. So my first step is to go to moles first. So there's moles of O2. There's 2 moles of what I want, the iron 3 oxide. And there's 3 moles of what I started with, the O2. And then it's 159.69 grams per mole. Okay, top one and the bottom one. The top one ends up being about 12 grams. The bottom one, starting with the oxygen, turns out to be about 16 grams. Okay, so which one's the correct answer, top or bottom? Top, so I turn out to make 12 grams because I'm picking a smaller number. What else will I need? Let's see. So that's the mass produced. The question B is, let's try to do this just by looking. What mass of iron is left over at the end of the reaction? 0, because it's the limiting reactant. Okay, so you just write down the number 0. But oxygen is not going to be completely used because it's in excess. There's a little too much of it. That one, you actually have to do a calculation. This is part C. So how much is left over at the end of the reaction for oxygen? Start with the correct answer, grams, and this is of the iron 3 oxide. Okay, now you want to go back to the oxygen. So you're going to say, well, there's on the denominator 2 moles of the iron 3 oxide. And then in the numerator, remember we're going to oxygen. So 3 moles of oxygen. And, oh yeah, yeah, that's genius. Okay, hold up, and then I'll get to you. 159.69 grams per mole. Okay, so that was a little backwards. What was your question? That's a good question. Does the 0 here have infinite sig figs? I usually report it as the number of sig figs we start off with. So if it's 3, then I report 0.00. But I'd really accept anything on that one. So if you put just the number 0, that'd be fine with me. Okay, so this, I should have flipped the order of these two. Okay, so now I have 3 moles of oxygen, and I need the mass of oxygen. So that's 32.0 grams per mole. The mass of oxygen turns out to be 3.60 grams. Oh, wait, is that what did I get that right? 3.60. I think that's right. Yeah. Of oxygen. Now I need to think, before I go on and actually try to report an answer, I want to go backwards and see, does 3.60 make sense from the question? Is that reasonable that my answer is smaller than the given number? It better be, yeah. This is in excess, so I have more of this than what I need. I only use 3.6. So yeah, you can see I have quite a bit excess. I would say 4.80 minus 3.60 will tell me how much I have in excess. 1.20 grams remaining.
1.20 grams.
Okay, now I want to double check to make sure that's all correct with sig figs. So let's see, in the question, both of these were 3 sig figs, so both of my masses are in 3 sig figs. When I go over here, this is in 3 sig figs, and my given number will have 3 sig figs. They both have the error in the same position, so 3 sig figs and the answer looks okay. Okay, that was my limiting reactant problem. Let's see. Let's try out a simultaneous reaction problem. And I think I saw an old one in here that looked pretty tasty. Okay. Okay, oh, yeah. Yeah, this is cool, I guess. Not as tasty as I thought it was though when I first saw it. That one's okay. Yeah, that'll work for you guys. Okay, here's one. Here, this is page 41 of the reader. Practice exam reader. Right there. In this problem, I mostly just wanted the intermediates. Let's try this out and see how this works. Okay, so in this case, I posed the problem a little bit differently. I didn't give you the overall reaction. You're only seeing the simultaneous or consecutive reactions here. So you need to put a little thought into what could possibly be an intermediate. What does it look like cancels out? Yeah, do you see the two CLs cancel if you just add them straight? Oh, this pen looks terrible. Okay, I don't want that anymore. Okay, what else cancels? Yeah, CCl3 here cancels. Okay, so those are the most likely intermediates. And then really, if I wanted the overall, so this is going a different direction where I don't give you the overall and I ask you for it, then you would just need to add it up, where the Cl2 plus the CHCl3 goes to the HCl plus CCl4. Okay, so this is another way to do a simultaneous reaction problem than what you saw me do in class. I have several examples online. If you happen to, unfortunately, see the manganese example that I posted online, if you think you're super smart or want to work really hard, you can take a look at that, but that was a pretty confusing one for students. But otherwise, the other examples are pretty normal. Okay? My manganese example is probably the toughest one if you look online on YouTube. It's one of my simultaneous reaction videos. Okay? Let's continue. Let's see, we wanted to see a little bit about molarity. Molarity, since I didn't get a lot of information, let me just do a quick overview on molarity. Remember, there's three possible problems. There's the unit problem, there's the dilution problem, and then there's the stoichiometry problem. I can tell you right now, the stoichiometry problem, what did we also call that? Yeah, it's also another way that this is called as a titration. What did I say to the poor soul who asked me about titration? Right, yeah, so it's here, but I'm really counting it in section 5.7. Okay. So, you would have stoichiometry though, definitely. Okay, so for the unit, really all you're looking for, both of these have one compound of interest. This is just where the molarity and volume is changing. This one you recognize, basically there's some sort of conversion. So if it's the first scenario, if it's a sort of unit sort of problem, basically we would give you, say, some sort of compound like, let's say, magnesium chloride, for example. I would say I have 5 grams of it in 1 liter of solution. And I want to know the molarity. This is a conversion problem. So you go, say 5 grams. You'd have to multiply by the molar mass. I'll let you find that. And then that would be the moles, and I'd have to divide by the volume, 1 liter. So it'd be that kind of problem. This would be the molarity of what? MgCl2. What if I wanted the molarity of just the chlorine? Yeah, if I wanted the molarity of, say, the chlorine, I'd have to say there's 2 chloride ions in every 1 MgCl2. So this would be the concentration or the molarity of the Cl ions, because there's 2 of them. Oops. Okay, so it's a pretty common question where we ask you of an ion, and if there's more than 1 ion, you need to multiply by that number. And you should have seen stuff like this on the homework of this chapter. So in this case, it's just double. If it was aluminum chloride, AlCl3, you'd multiply by 3, and so on. Okay, for the dilution one, there's sort of one way. There's some tough problems. I'll see if you ask me from the practice exam. But if it's a pretty normal problem, let's say I have 6 molar of the MgCl2 again. Okay, and then let's say in 100 milliliters, and then I want to change this molarity to 2 molar. Then I could do a little calculation. I see the molarity is changing, the volume must change. So I would say, well, M1V1 equals M2V2. Let's get a different color here for the finish here. This would be 6.0. This would be 100 milliliters. This would be 2.0. And this would be question mark. So what's the final answer here, V2?
300.
It'd have to be 300 milliliters, meaning, another way to say this, if the molarity goes down by 1/3, I have to triple the volume. Okay? Or another way I could ask this, how much did I add? And I added, in this case, 300 minus 100 or 200 milliliters of the water. Okay? So the two ways I can ask about a dilution problem. You'll notice sometimes we don't even have to give you the volume. So we'll just say, I started off with 6 molar of the solution, and I tripled the volume. What's the new molarity? You don't even have to know the volume. If you know I tripled the volume, then the molarity must go down by 1/3. Okay, so that's molarity. Let's cross that off. For percent yield, was there a particular, do you want me to just a little overview on that? Okay, there's the easy question and the hard question on these. The easy question on percent yield is as follows. It's just what's the percent yield? And I give the actual, and you have the theoretical. Okay, numerator or denominator, which one is the one you calculate? The bottom of the denominator. The numerator is the one done in lab, which on an exam is the number we give you. Okay, there's maybe two slightly harder versions of this. If I rewind for a second, let's see, where did I write? Yes. Remember this problem here? The mass ended up being 12, remember that? If sometimes for fun we want to mess with you, and I'll say, I've got 10 grams here. So I'll say, we did this experiment with both of those, and I get 10 grams at the end. And even though I give you the grams of the product, I'll ask you for the grams of the product. Okay? What I mean is, the number that I just gave you is the actual, and I want you to calculate the theoretical. So I'll give you the mass, but that's not the mass I'm talking about when I ask the mass. Does that make sense? So I'll say there's 10, but that's really what we got experimentally. I want this number right there. Okay, that's one way that we freak you out. Was there a question on this way? Yeah?
I have a practice sample for the sample.
Let me just take a quick peek at it. This is not that though, but I can do this afterwards. This is a combustion analysis problem. Yeah. Another style of the percent is if I don't give you some of these masses, and I'll say, for example, I'll say something like, oh, the percent yield was 65%, or something like this. I think there was a homework problem like this on the extra credit. Then I have you use this number to work backwards. So you'll see that's a pretty common variant as well that you'll see on the practice exams. So we give you the percent yield, and we want you to work backwards to get one of these numbers over here in the reactants. Okay? So those are the three variants. The easy version is just a straight up calculation.